So this time we're going to go over how to do natural deduction in AXolotl. We'll use one of the famous statements, one of the statements which is a bit weirder to prove in natural deduction than maybe, let's say, sequent calculus, which is the double negation of a prepositional variable implies the prepositional variable. So, and those of you who are used to sequent calculus know this is actually quite a simple thing to prove in the sequent calculus. As you see, those of you who are familiar with natural deduction will realize, yeah, okay, it's a little bit harder in natural deduction, but it becomes quite clear if you think about it. But let's see how clear it would be in AXolotl. So let's say first we're going to reduce the font a little bit. So this is a more reasonable font size. And like you would do in the sequent calculus, the first thing you would do here is probably the implication elimination on the right. So here goes implication elimination. We just choose the formula. And all it does is it moves the x to the left-hand side. So let's do the implication elimination. As usual, nothing's very special here. We just get to see how the variables match up. Everything's matching fine. And now we have the not p on the right-hand side. Now, unlike what you would do in a sequent calculus, we have to use the rule which is called contradiction. So to do a contradiction, we have it right here. What we do is we just take the atom p, and we're going to say, well, let's assume not p, and we know that not p will derive to bottom, right? So now the idea is that from not p, if we reach bottom, bottom could introduce anything, so we get p. So let's go to and try this out. So, okay, the matching here is quite simple. Nothing special happens. So now we have that negation. And right after doing that negation, the question is, well, what do we do next? All right. The important thing here is that we have to prove that negation. And one way to prove that negation is using another negation here. So what we could do is we could do implication elimination rule. So let's try the implication elimination rule. All right. Well, what that will do is, if you see here, we have something implies bottom, and we have something. So negation could be thought of as implication of bottom. So what if we just put in not p, right? So let's try that with not p. So what you see here is that we have this not p implies bottom. We don't have any, on the left-hand side, we don't have any bottom, so we have to turn this negation sign into, or this bottom into a negation. So we have this rule right here that I just selected. All right, okay, I have to select the goal. The AXolotl is reminding me. So if we select here the goal and we just scroll across, what we see now is that, okay, we have not p and not p on both sides. And then the other one we have not p and not p on both sides. So the question is, okay, so what do we do next? So obviously this not p and not p, we say those are axioms, and we could just use the axiom rule and remove that. All right, good. Axiom rule is removed. In this other case, all right, if we were to select the rule that we want to use, the axiom rule, we see, like usual, it's not applicable. So how do we make it applicable? Well, we have here the ability to change the position of the formulas on the left. So let's just apply that. All right, we see everything, how it's matching. There's nothing in the z, so we just switch everything around. And now we have the formulas in the right position. We could apply the axiom rule and we get, let's see once more. Now we get, congratulations, we have finished the proof. So let's go see what that looks like. So if we go to the view proof mode, we could see here the contradiction being applied, and we could see how it just uses the same format as a sequent proof, except for now what we see is that we have these natural deduction rules. So if we were to go over here to save proof, we would be able to save this proof like would be in sequent calculus. It's just that we have different rules in this case. And that's it for now.